All right. Hello, everybody. My name is Jalal Difala. I hope you are having fun at Wisdom. I couldn't make it, teaching and stuff. I'm still in this mode of pandemic schedule where I have meeting, talk at crowd science, meeting. So anyway, I'm very excited to, give this talk, which is about a new paradigm for crowdsourcing for Wikipedia editing, which we coined machine in the loop. So again, I'm Jalal Difala from the Collaborative Intelligence Lab at NYU Abu Dhabi. This is the first time I actually give this talk. It's basically I'm putting together a work that I've been working on together with my students at the NYU Global Network, together with the Wikimedia Foundation as well, collaborators at various universities, and also with Wikipedians. Okay. So before we start, I would like to give a bit of an overview of where I'm coming from. So I basically started with crowdsourcing really around the time where Amazon Mechanical Turk was popular in order to enhance machine learning via obtaining labels from humans. So I have worked on a lot of systems where we were improving, entity linking, instance matching, etc., by asking humans to perform human intelligence task on Amazon Mechanical Turk. And it was really great times at this point. And I want to sort of emphasize that things have changed and we started talking about creating more kind of complex systems where we have like this paradigm of human in the loop, where there is a huge machine learning or huge information system that is involving the crowd at some point during its execution. But this is really nice, but what I would like to sort of transition into is this notion of collaborative intelligence. Obtaining labels from humans is really good for improving the machine learning execution, and this sort of serves specific purposes. But can we harness the power of machine learning back in order to improve humans, make them more productive, help them in their daily tasks? So just as a reminder of crowdsourcing via an API, where you have on one side a task requester, and on another side you have a crowdsourcing platform. Toloka is one example. You have a programmable API. The task requester can create an interface, specify instruction, create a structure for the tasks, design the reward. They can design more sort of interactive interface, etc. This is pushed to the crowdsourcing platform, and then the humans will pick up the task, they perform the action, and then they will submit their responses back to the requester. This is the usual paradigm that we know, and we try to improve over and over in our community in the last 10 years plus. And here really the research challenge have been focusing about the quality control. How can we remove sort of uncertainty that is attached to the answers that we are obtaining from anonymous users behind this black box, which is the crowdsourcing platform. So we worked on a lot of different aspects in this space, from creating specific incentives to having different reward schemes, to tailoring the task and the interface to a specific task. Modeling the user and their knowledge, modeling the user and their skills with respect to the task. Problems such that task routing, or identify which worker will be best fit for a particular task. Other aspects include, having repetition, where we ask multiple workers and aggregate at the end, using majority vote or more advanced schemes. We can also think about problems relating to adaptive replications. Like we can ask one worker, and then if we are uncertain, we ask a second, and then we have this evolutionary step in order to obtain more and more responses to improve the confidence of the labels we are obtaining. But then I'm going to make a point of having the ChatGPT slide in every talk I'm giving in the future. All of these tasks, or many of the tasks that I've been working on in the past, now can be to some extent, already solvable by, machine learning systems such as ChatGPT. And like we are not like solving all problems, but we are achieving really good results in terms of named entity recognition, in terms of entity linking, in terms of extracting relationships from text. So we've done a lot in terms of machine learning research, right? And to some extent, I like to think that all of this progress was thanks to the crowdsourcing effort we've been doing in our community, because a lot of the data sets were created using crowdsourcing. Large language models, of course, they use internet content, but a lot of the very, clean content would be extracted from places such as Wikipedia and Wikidata, which are essentially crowdsourcing platforms. And in this context, I would like to highlight, the projects that are related to Wikipedia, which are under the general Wikimedia infrastructure, such as again Wikipedia, Wikidata, Wikispecies, Wiktionary, etc., and other projects such as OpenStreetMaps, which are also crowdsourced. One thing that I'd like to emphasize is that in all of these wiki type of platforms, everything is crowdsourced. Okay, so down to the community interaction or self-organization. Every content you find on Wikipedia was actually added and vetted by a human, which is like a huge revelation when you think about the scale to which these platforms have evolved over the years. So if you were to look at the numbers, Wikipedia, if we just look at the English Wikipedia, we are talking about 6.6 million articles over the last 20 years, right? We have 30,000 monthly active editors. We have 5 million monthly edits that these editors are making. And all of these kind of actions or additions to the platform made by the editors is consumed, extremely heavily. We're talking about 15 billion monthly page views. So we go from this one or few to many paradigm, right, to this many to many paradigm, how humans can put together crowdsourcing work in order to benefit the rest of humanity. So this is a graph that I like looking at and try to understand. And I acknowledge that I need to do specific research to understand exactly how things evolved over the years. But one thing is really clear to me. This graph shows the evolution of Wikipedia from its inception to 2019. And every line would represent the number of active editors, split down into three categories: those that make 5 edits and more, 25 and more, and 100 and more. Okay, so for very active editors with 25 or 100 and more edits, you have this slow start and then stability over time. So we have a stable pool of humans that are actively editing to Wikipedia. And then on the other end, you have this other category, which is the 5+ edits, that started very quickly at the beginning and then started slowing down and plateauing. I liken this initial high speed, ramp up in terms of activity or active editors to the fact that Wikipedia was really starting and there was a lot of low hanging fruits around the site, very, small things that can be added. I can add a new article because it didn't exist around physics or astronomy. So you have these very low hanging fruits actions that humans or active editors can do at that time. But when it starts being really serious, like adding, heavy content, putting more substance into the articles, I will associate this more to the active editors who are more experienced and that would make more edits to the site. And I will come back to this realization later on. Over the time, Wikipedia, became more and more complex, right? If you look at the Wikipedia page, it is human, legible. It's written in English or some language. It has some structure. You have an abstract and a bunch of sections, right? So you can consume an article by reading it. But if you were to take a step back and look at the big picture, how are the articles connected to each other? You start having this hyperlink structure of articles and how they connect to each other. The different colors you see here are basically categories of Wikipedia articles. The nodes are articles, and the link is basically a hyperlink from one page to another. So why I'm talking about this is essentially to highlight the fact that if we go from text to graph, the capability of a human to understand what's going on and what is missing, what are the areas of development, what is kind of already oversubscribed to, what are the articles that are underlinked, etc., will make things a lot more complicated for humans in order sort of to contribute if you want to sort of add specific actions to specific articles. Okay, enough about Wikipedia. I'm going to talk about Wikidata. So Wikidata is another crowdsourced project. And like Wikipedia, Wikidata is a bit of a mix. You have half crowdsourcing and the other half automated scripts. But these scripts were created by the crowd. So they want, for example, to import a certain database. They will write a script, and the script will pull data from that database and push it into the Wikidata. It's actually under some level of control. Last time I looked at the number, if we look at the aggregate of actions made by bots versus humans, we are really at the 50-50 in Wikidata. Nonetheless, Wikidata is, as of today, around 102 million entities. It involves 24 monthly active editors who make 15 million monthly edits. These numbers are not too shabby and very much comparable to the figures we've seen with Wikipedia English, actually. So Wikidata is like a really active knowledge graph that is being developed by the community, which is somehow surprising to me. If you were to sort of think about what a knowledge graph is, this is a knowledge graph. It's essentially a graph that is heterogeneous. You have nodes representing entities. Nodes can be connected to other entities or can be connected to literals, strings, integers, or images, etc., etc. So what you see here is not just some abstract representation, it is the data itself. So a knowledge graph is a graph. And as a graph, it's not really made for human consumption. In fact, as a knowledge graph, it's really made for machine consumption. So what is surprising for me is that how would a human sort of be able to contribute to a graph creation, specifically when we get into very large scale setups with millions of entities and billions of edges connecting these entities, right? So specifically going back to the challenges that I highlighted with respect to Wikipedia, there will be a lot of places where we have knowledge graphs, underrepresented entity classes, et cetera, et cetera. So how can a Wikidata editor sort of target their effort in order to enhance the site in the right direction, or the knowledge graph in the right direction? So I would like to pose this sort of bigger or broader question, which is 100% crowdsourced content scalable at all? And I like to think that the answer is it depends. With the current tools that we have, it is very hard to scale, right? And keep up with the information deluge that we are facing in order to add new entities that are emerging, facts about these entities, et cetera, et cetera. So the interface in itself does not help. And not only that, there are many factors. Factors can be categorized into technical. What is, like, if I come to the site, I want to contribute something new, I have to learn the language, the wiki text language in order to write the article itself. I need to understand the interface and multiple kind of small details, like we can put them under the technological barrier in order to contribute to the site and be part of this crowdsourcing effort. And then there are the conceptual problems. Like, I need to understand what is possible to do on the platform and what's not possible to do. For example, what is notability? I'm going to create a new article on Wikipedia, and then it will be reverted because the article I'm writing about is not considered notable enough to be worthy to be on Wikipedia. We don't have this problem in Wikidata, but we have other problems such as references and like authoritative sources about the entities and their relationships. And then you also have cultural problems, like it's a community, and as a community, you have a variety of individuals who are interacting with each other. There are talk pages, they start some debates sometimes, they're not agreeing in many cases, right, when it comes to editing articles and also entities. So we have this kind of problems, and we want to sort of solve them somehow in order to be able to scale further from where we are in terms of numbers. Ideally, like, such a problem will also deal with problems related to growth and diversity of contributors. The numbers right now about contributors are not encouraging. most editors are men from North America and Europe, based on recent surveys. If we were to think about knowledge equity, which is like the accessibility at all into the platform, so the idea here would be to break down the social, the political, and technical barriers that are preventing people from accessing and contributing knowledge to the platforms, again, whether Wikipedia or Wikidata. So the idea really here is to kind of try to get some lessons learned from crowdsourcing and human-in-the-loop words into this crowdsourced editing setup. So the idea would be to break down the editing process into simpler tasks. So I know what you're thinking, from micro tasks to micro editing. In fact, this particular term was on the table, but we decided otherwise. We call the tasks that we work on structured tasks because they put humans who are contributing content to wiki projects into like a flow of tasks they can perform. Okay, so in order to design such structured tasks, we came up with a formula which we call machine in the loop. Unlike human in the loop, where there is some machine, learning or information system that uses human intelligence at some point in its process, here the end user, like the real driver, is the person itself, the editor, and then the editor is aided by AI. So the machine in the loop formula goes as follows. The task is attempted at scale first using machine learning, and then the editor simply verifies the output and validates the operation. Okay, if eventually, like the task or the action will be committed into the database from the human itself, but it was attempted by a machine learning algorithms before that. So you can think of it as a kind of a recommender system that is, piloted by the editor. And in this process, the editors get more exposure to editing tools. So slowly, they will learn about the wiki text language, they will learn about the tool itself. In fact, we are sort of more targeting newcomers or new editors, right? So we recall this graph, this curve about editors who are making just few tasks. We want to sort of reignite this particular type of editors, those who are willing to contribute, but they can only perform few actions here and there sometimes. Okay, so we want to create structured tasks to target newcomers or users who are willing to perform few tasks over time. Hopefully, we want to kind of retrain our machine learning and AI models using the human feedback. So it's not only like yes or no type of action, but there is also a feedback that is given back to the machine learning, and we capture data about that. When we break down like the complex editing task into a small one, what we can do is also modify the interface itself. So we can think about creating mobile-friendly tasks that at the end are pushing information into a wiki project. Okay, I hope this sort of clarifies a bit the idea of the formula behind structured tasks. And we apply structured tasks to two types of projects: editing in Wikipedia and completing Wikidata. So all of these are structured tasks that have been deployed or are actually under development. So I will cover a couple of examples of structured tasks in these lists. And yeah, I will start with add a link. So the structured task here is about identifying content to interlink. Okay. This means that we want to identify linkable substrings, not only named entities, right? And then identify a target article. So that's your basic entity linking problem in Wikipedia. Okay, so the problem goes as, we extract a snippet of text, you identify a particular substring, you identify potential links, and then you perform the entity linking to subtasks, which are essentially link disambiguation at the end. So entity linking is an established problem. We can break it down into these three different steps: mention detection, link generation, and link disambiguation. If you focus on named entity recognition, you can replace the mention detection by a named entity recognizer at the top. Okay, so entity linking is heavily worked on. There are plenty of research papers in this subject. I've worked on this problem in the past. But what we don't know is that, when it comes to entity linking, oftentimes the benchmarks like heavily focus on English, right? Instead, in Wikipedia, the goal is to have such an entity linking system for low resource languages and eventually for all Wikipedias. In fact, Wikipedia English was not really the target at all to start with. We use it in our experiments simply to validate our model, right? But the goal is really to have an entity linker for all the languages. And when it comes to low resource languages, for example, Swahili or Taghbalit, it will be very hard to have a machine learning model that is precise enough. Even ChatGPT will not be able to scale down to these kind of low resource languages unless we have enough data once we, populate these databases over time. So we want to have a system that supports 300 plus languages, which are basically the Wikipedia projects that are in place. On top of that, and which is not always reflected in entity linking tasks, you have also other considerations that are Wikipedia specific. You have to adhere to the manual of style, and there are many constraints. A simple one that is, the same across all the project is, well, if you link an article to a particular article, you do it once in one page, in one article. Okay, you cannot have multiple links to the same article in a web page. So you have this constraint: where should I put my link? There are other constraints that are heterogeneous across the projects. So one language would say, okay, I can link a date to a page about date statistics. Another project says, no, we cannot link dates, right? So you have plenty of things that are, or rules that are present in the manual of style. The other consideration is that, sure, we can train complex transformers, et cetera, to perform entity linking, but we prefer simpler versus complex models. First of all, we need to scale. We are talking about 300 languages, right? So this is very, very large amount of data to go through and identify possible links to extract. And also you have the transparency aspect. The models should have some level of explainability. You have to tell the user why or what is the reasoning behind extracting this particular link. And then you have to have like some form of utility, that is finding a balance between precision over recall. The idea here is that because there is a human that is overseeing what the machine learning model have extracted and recommended, so you can lower a bit the bar of the precision, right? So you have more recall and then more opportunities to identify links between articles. This is really useful for low resource languages. Okay, I'm not going to go too much into the details of the pipeline, but we created an end-to-end entity linking system that uses mention dictionary, that is essentially a dictionary of surface forms against all articles, against all Wikipedia languages and their consideration. We have a sweeping window that goes over a paragraph that identify potential matches. And then we have a constraint checker that is basically a set of rules we extract from the manual style. And then we have a bunch of features that we engineered manually, going from graph embeddings to sentence embeddings to Levenstein distance. Like we have a bunch of features. And then at the end, we train the classifier to essentially give a probability of all the potential matches for a given sentence or snippet of text. These potential matches are then pushed to a UI that is controlled by a human that eventually says yay or nay for a given link. And they have the possibility to give a feedback that we record and we use for retraining the model via human feedback. So the model itself is extremely simple. It uses boosted trees at the end with the features, right? In order to evaluate this, we did back testing. That is, we extracted from a battery of 6 languages, pages, links, and anchors. We had a training and test protocol. And then as metrics, we looked at the precision, recall F1, and we also looked at N5, which is the number of articles for which we generate at least 5 recommendations. The idea here is that if we are parsing an article, if we do not find at least 5 potential links to add, it's not worth pushing it to a human editor. The reason is that if you are a human and you spend time reading the article, you don't want to perform only one action. Like, we want to maximize the number of actions a human can perform on a given article. So this sort of pushes the utility up of the process. This is just some results from the backtesting protocol. Because the model gives us a probability back, we can sort of play a bit with the threshold. And we consulted with the community to say, okay, well, here's the backtesting protocol that we did. How are the different values that we obtained? What is the reasonable threshold you should utilize in order to maximize the utility? And for many languages, 0.5 seems to work quite well. You have a precision of about 0.7 and a recall of about 0.3. So this is good enough for a lot of languages. So you have plenty of articles with at least 5 or links extracted and with potential links to be added. In some cases where, for example, here you have Bengali, where 0.5 was not enough. We only identified 3,000 articles with at least 5 links to be added. So what we did there, say, okay, we can reduce the probability threshold, and the community was fine. Say, okay, well, 75% precision, we can work with that if it gives us more opportunity to contribute. There is still a human that is performing the action, so that is totally okay. And after the backtesting, we pushed all of these to actual expert editors who, for which we created their own data sets. So we extracted articles, we run our pipeline, extracted links, and we asked the expert editors, those whom we know and act as ambassadors for particular communities, to rate our links. And we were very surprised to see that the precision was actually bigger, or at least similar to the one we had with the backtesting protocol. So from there, we sort of were encouraged to go forward, and the system was actually handed over to the machine learning team. I have no responsibility in this part where they created large scale deployment of our machine learning algorithm that run across the whole Wikipedia for a given set of languages. So this runs in batch. It extracted all possibilities and pushed that to a UI. So the UI looks as follow. It's basically an article where you have annotations of links. The annotations have like this flag that the annotation is proposed by an AI, right? And a human can say yes or no. When they say yes or no, they can add an additional feedback that we collect or designed for this particular task. There's a task or an edit summary. And at the end, when the user pushes, publish, the publication itself is associated to the user. So in some sense, we are sort of improving or boosting their productivity using this process. Okay, so there was a time where the tool was evaluated using A/B testing, right? So there was a team called Growth Team that created 2 subgroups, a subgroup of newcomers that arrived to the platform, and they are given, add link type of tasks that use the structured task interface that we created, versus users that utilize the old visual interface or Wikilink interface. Among these 2 groups, what we saw is that the number of edits made via the structured link, the structured task was almost 10-fold bigger than those performed via the baseline or the uncontrolled group, right? The number of reverts was higher, but proportionally it's actually lower, right? So you have 7.5% of revert rate, where revert rate is another sort of more experienced editor sees the edits made by the newcomers and say, okay, well, this should not have been added, or it should stay there. Okay, another sort of parameter that we were a bit nervous about, which is the over-acceptance rate, which is a problem that we see in crowdsourcing, where you give a task and you have users that can click yes, 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 yes continuously. So that's the over-acceptance rate. So just looking at the data, this particular behavior was observed among 8.5% of the population, which is quite encouraging as well. And we can also sort of try to implement strategies to avoid that using attention check or switching modality of tasks. Additional aspects here is that we have had higher task completion rate over time. So like this was like the 8-week pilot study was done 2 years ago, right? And now the AdLink process or infrastructure is deployed across, I think, more than 20 languages. And over time, we saw a lot of engagement from the newcomers with this particular task modality. And has been like an overwhelming positive response from the community. So yeah, that was like a first success with a huge deployment that's been running now for 2 years. And yeah, so we continue now with additional structured tasks. Now I'm going to talk about content translation. The structured task is about identifying sections to translate from source language to target language, right? So this is essentially a map to highlight the problem, right? So if you put a light bulb on every geolocation tagged on articles in Wikipedia, this is how the map would look like. And again, it will be very, very difficult to identify knowledge gaps if you do not have sort of automatic tools that will tell you, well, Africa is not well covered on Chinese, Wikipedia is not well covered in South America, et cetera, et cetera. So Wikipedia has a content translation team who created the interface for us in this time. So there's this content translation tool that already exists, right? So the content translation tool gives you on one side the source language and the other side the target language, and the user has the interface and the abilities to sort of translate from one language to another. It is possible to say, okay, well, the machine learning part is about utilizing a translation tool or translation service. We can piggyback on that. So the question is that, okay, well, the interface is here, the machine learning part is not problematic. What is the structured part? The structured part is about breaking this process down to simple tasks. The content translation tool is about translating the whole article. But what if we were sort of to focus a bit more down to not the sentence, but perhaps to the section? Identifying sections that need translation is what we call the structured task related to content translation. So then the question is, what are the sections that are missing translation? If you have an article that is completely missing, it's easy. Take, I don't know, English and then try to translate every section. But if you look at say, for example, here, universe entity across multiple languages, and you look at the sections that exist in these languages, it will be very hard to actually align the sections and identify which section maps to an existing one. So there is no need for translation, and which sections are missing and would require or would benefit from a translation or the attention of a human. So we map this problem into an instance matching problem. Right? So the instance matching is about what particular sections from one language map to another particular section in another language. So, well, this turns into like a graph problem again, where nodes are sort of section titles from particular languages. I'm not going to go too much into the details here, but to just give you an idea, what we use here is essentially machine learning algorithms where we have pairs that are connected probabilistically. And then we have two types of pairs, like pairs coming from the same language, and this will be sort of synonyms, right? For example, awards and recognition is a synonymous in award and honor. And this will be a translation to récompense and distinction in French, right? So we can obtain this particular pairs, right, by asking the crowd to match things that we are missing. And then we run like a machine learning pipeline that will sort of refine these pairs establishment between the different sections across the articles. Now, I guess the question you're asking yourself, okay, well, this is a translation problem. If I take a section title, I just run it through a translation service, and it gives me the mapping. It's true, but it's not quite correct. The reason is that, back again to the manual style, some communities name their sections very specifically, right? You cannot sort of take awards and honors, translate it, and say, well, awards and honors maps to this in French, and you should use that. The French community will say, no, this is what we call awards and honors in our community. Okay, so we have like a mixture of two pieces in our model. The first one is sort of similarity-based model, right? The similarity is built upon, you know, a bunch of features that we extract. Like we have the section content similarity, we have the title similarity, we have embeddings across the titles, etc. And on top of that, we have a probabilistic soft logic framework. This essentially is a machine learning model that adds constraints that are declaratively added to the model. This constraint tells you, for example, that one section title is synonymous with another section title in one particular language, right? And then this section title is a translation to another section title in a different language, right? So you can add this kind of rules to the probabilistic soft logic framework we have to enforce certain level of rules. In order to obtain, seed pairs, what we did is we created an interface for crowdsourcing, right? So we ask bilingual experts on Wikipedia to give us translations from one particular language to another, right? So we created a crowdsourcing interface, reached out to Wikipedia volunteers who declare, a set of languages in which they are, fluent, and they add such data to the training process. This is just some figure about the number of pairs we obtained across languages. If a pair is missing, is that we did not find like editors who are fluent in that particular pair. So we obtained plenty of data essentially in order to bootstrap our machine learning model with the probabilistic soft logic, and also to evaluate our model later on. Okay, moving away, let's see how I'm doing in time. Okay, so moving away a bit from Wikipedia, I'm going to talk about some structured tasks we worked on in Wikidata. The first one is Wiki2Prop, adding facts to Wikidata. The structured task here is about identifying missing properties to populate in Wikidata. So as I said earlier, Wikidata is a knowledge graph, right? So you have nodes that are interconnected with relationships. In a knowledge graph, like the representation is that you have a set of vertices, and then you have a set of relations connecting to a set of vertices, right? So it's entity, relation, entity. So the set of entities can be very large, no problem, but also the set of relations can be very large. If we look at the set of relations in Wikidata, it's around 8,000 different relations that can be established between two entities. This is somehow controlled. You cannot create a relation out of the blue. It has to be part of the ontology to some extent. So if you think about the problem is that if you go to a particular Wikidata page and you want to enter a new fact connecting one entity to another one, so you have to have some knowledge about the ontology, right? So this adds an additional layer of complexity to onboard newcomers. Like as a newcomer, I would have no idea about what are the properties, how I should connect them. Okay, so if I do not know the relation, I have less chance of adding this particular relation. So what we decided to do is to create a recommender system that would extract and rank potential properties to be added to a given entity. So we are not establishing a link, we are just saying, okay, here is the ranking of potential properties to be added to a particular entity. The way we do it, we start from the entity, we get rich information about this entity from Wikipedia. So you have text and image, we run it through on your network, and we have our ranked list of properties for a given entity. Our system is basically a multi-model fusion network where we take in multiple languages for a given entity and also multimedia data, specifically images, to perform this. So we train an architecture specified as such. Okay, in terms of structured tasks, so we talked about the machine learning, the intent. The interface is basically an add-on that we developed for Wikidata, where you go to a particular entity, you activate the add-on, and it ranks the potential properties that can be added. It doesn't do anything for you. Again, it's Wikidata, so you have to add this fact yourself. So just gives you a ranking of potential properties, and you have to click on add claim, and you add this particular claim to the entity. So you see how this sort of improves the productivity for the humans and adds relevant data to the platform accordingly. So what's next from here? So Wikidata and Wikipedia is a subset of Wikidata. It's almost like 6% of Wikidata, which means that we are simply, by going through our protocol of taking text from Wikipedia and images from Wikipedia, we're essentially making rich entities richer, right? So there is a huge pool of entities that we are not targeting at all with our tool. And in the next work, we try to cover that. And this work is essentially about finding more fine-grained information about what we call orphan entities. Orphan entities are entities that are not notable enough to be in Wikipedia, but have been mentioned to some extent in Wikipedia. And in this process, we basically try to extract some textual information from Wikipedia that is related to a particular entity that is not necessarily a Wikipedia page in Wikidata. And then we go through the same process as Wiki2Prop in order to rank entities. Without going too much into the details, the program works as follows. We embed not articles, but we embed down to the level of sections and subsections. So we have these embeddings for textual content, and then we have knowledge graph embeddings, and we try to merge them into like a unique or uniform vector space representation. And from there, we have our matching from entities to text. So I'm going to skip some of the details. So at the end, what this program, which we call paragraph, is essentially linking graph entities to specific mentions or paragraphs inside of Wikipedia. So this sort of enriches orphan entities with textual content, right? And again, as I said, this will be pushed back to Wiki2Prop later on for property prediction. I think I'm a bit short in time. The next structured task I wanted to talk about is on question answering with knowledge graphs. So the structured task is about identifying missing information in a knowledge graph through conversation. Okay. The idea here is to essentially have an agent with whom the editor is interacting. The agent is answering questions from the graph, questions that are factual, right? And then a human will eventually give feedback to the agent based on how well it is answering the questions. So I'm not going too much into the details here. I'm short in time. In terms of interface, this is still under the works. I have students who are working on different small parts, but the idea would be to sort of, again, have an interface to populate Wikidata or actually OpenStreetMap as well with the crowdsourced content via a chatbot. So this is still under development. Okay, so this wraps up a bit the structured tasks that I've been working on together with my collaborators on Wikipedia and Wikidata. To wrap up, and as a conclusion and future work, so we introduced this new notion of machine-in-the-loop paradigm, which is really about empowering crowd editors with AI tools. Okay? Then we came up with this new notion called structured task, which is essentially a formula of having a human editor, an interface, and an AI that is hashing through a large scale, knowledge base or content that is, otherwise very complicated for a human to sift through in order to give them some recommendation of where to go, right? And following this particular formula, we were able to identify many potential, areas of development. And really, this sort of changes the way Wikimedia Foundation thinks about the development of Wikipedia, right? So we are going from this interface-only interaction to new forms of editing content and contributing content. Of course, from a machine learning perspective, there is a lot of improvement there, specifically on leveraging the user feedback that is giving back to the AI that is making the recommendations. Of course, there are many other structured tasks that are in the works. There's this Wikipedia image caption challenge that was run last year, which is about adding captions to images. So I will stop here. I think I'm a bit over time. Hopefully that is fine. If you have questions, please